Dear students, now we are going to study one example of Maxwell's-Boltzmann distribution function that is used to find out the molecular energies in an ideal gas. Okay? So we are going to discuss about the molecular energies in an ideal gas. Gases. Okay. So this we are going to discuss. Okay. So here we know that this ideal gas, the molecules in an ideal gas, they obey the Maxwell's-Boltzmann distribution function because they are distinguishable particles and their wave functions do not overlap, or you can say they overlap in a negligible extent. So we can use the Maxwell's-Boltzmann distribution function. Okay, distribution function. Okay, so now I am considering n number of particles. That means you have the ideal gas with n number of particles, and I consider this n is very large, and this n is very large. So instead of using our concept of discrete energy levels, we will use a continuous. So here our epsilon is a continuous distribution of energy, continuous distribution of energies. So what do you mean? If it is a continuous distribution, what we mentioned earlier, we instead of using G epsilon, what we have to use? We have to use G of epsilon, D epsilon, isn't it? Okay. So eventually, so we have so many levels, E1, E2, E3, etc., etc. So many levels, but they are continuous. They are not discrete levels. Okay. So if you have plenty of levels, or you have a continuous energy distribution, then you have to find out what is called the number of molecules whose energy is in between a certain value of epsilon to a certain value of epsilon plus d epsilon. So like here you wrote G epsilon, D epsilon. So then our number of particles having energy epsilon, having energies between epsilon and epsilon plus d epsilon. So that will come as here n of epsilon is equal to G of epsilon D epsilon into your distribution of functions, isn't it? Okay. So here we know what is f of epsilon, because these particles obey the Maxwell-Boltzmann distribution function. So you can just rewrite it like this. This is equal to f of epsilon is nothing but we already mentioned in the last class f of epsilon, that is the Maxwell-Boltzmann distribution function. Actually we mentioned as f suffix mb of epsilon. So I am just writing it. Fmb epsilon is equal to a e raised to minus epsilon by kbt. Okay, so I am here also I am using mb suffix mb, so that you won't get any confusion. Okay, so I will just replace it here. Then what will be a, the constant a, actually that depends upon the number of particles. We already mentioned that constant depends upon the number of particles in the system. Then G of epsilon, again the remaining is e raised to minus epsilon by kbt d epsilon. So this is the number of particles or number of molecules in the ideal gas that is having energies between epsilon and epsilon plus d epsilon. So you have to remember this is the number of particles having energies between epsilon and epsilon plus d epsilon. Okay, so this is the n of epsilon. So now first our aim is to find out the exact expression for this, because we just wrote g epsilon e raised to minus epsilon by kbt into d epsilon, that we will go. So now I am just erasing all those things. Okay, I will rewrite it again back. So here number of particles that is having energies between epsilon and d epsilon, that is, I am just writing it here on the side, that is n of epsilon is equal to a g of epsilon e raised to minus epsilon by kbt d epsilon. Okay, so leave it here. And here, you know, g of epsilon d epsilon represents the number of states that is having energies between epsilon and epsilon plus d epsilon. Okay, so that's it. Now we are going to in order to solve this, because if you want to get the total number of particles n, then what you have to do, you have to integrate it. Okay, so before going for this integration, we have to know what is g epsilon d epsilon, then only we can proceed it. And also we have to know what is the constant a. Okay, so I am just flipping now to a new space that is called phase space, because in your syllabus itself there is a phase space. So actually whatever you studied so far, that was all in a configuration space. Configuration space means like our Cartesian, or in a Cartesian coordinate system, or spherical polar coordinate system, or cylindrical polar coordinate system. These are all configuration space where you deal with the positions. Okay, so when we go to more and more and deeper into the physics, you need much more advanced space, like there are so many. So in this phase space, it is very, very important for our future studies. Phase space means it is having both the position as well as the moment. Okay, so the drawing a phase space is a tedious job, but we generally just draw it by taking the momentum axes only. Okay, so here you have in the phase space. I will just come to the phase space in details in the last part of the our module. Okay, so for the time being, what you have to understand, in the phase space you have 6 coordinates, 3 positions and 3 moment. Okay, like the coordinates are, you can write your position like x, y, z, then px, py, pz. So you have total of 6 coordinates. Okay, I will come to it in detail. If you have n particle, how many coordinates will be there? If you have simply 1 particle or 2 particle or 3 many particle, so all those things I will come in the last class about this in detail. So for the time being, you just understand phase space. It means it is having both the position and momentum axes. Okay, so I will represent our problems in phase space. That is, in the we will take the momentum axes. Px, Py and Pz. Don't worry, I will teach you more in detail, because here in our problems we are dealing with the energy. So you know these particles, or in the ideal gas, the molecule, they are in motion. So they obviously possess kinetic energy. Because they are in continuous motion, we cannot say the potential energy, they are in kinetic motion. So as you know, what is the expression for kinetic energy? Kinetic energy, or in total I am just writing the energy. So whatever the energy I am considering, it is only the kinetic energy. So kinetic energy is, we write half mv square, isn't it? Or you can write it as half, I am just dividing and multiplying with the mass. So that is divided by 2m, and in the numerator also there is one m and already mv square. That is, you will have mv all square by 2m. What is this mv? mv is nothing but your momentum, linear momentum. Okay, so we will write p square by 2m, isn't it? Then what about the p? The linear momentum p is equal to square root of 2m epsilon, isn't it? Okay, so just keep in mind your linear momentum is equal to square root of 2m epsilon. Okay, so I am just erasing it. So now I will just rewrite it here. My p is equal to square root of 2m epsilon. Okay, now this p in the momentum space, you can take momentum space like px, py, and pz, and my particle that is in a motion, it has a linear moment at this point. Actually this point is in the space. Okay, so if I draw a what is called circle, then you will understand, I think, in a better manner. Okay, so then I can now I will make, okay, then can you feel it is like it is called sphere? You can feel it. So here my particle's momentum, this at this point. So this is your p, and this small change that I am calling it as dp. This is actually dp. Okay, so I have a momentum p. Thus this is a sphere. That sphere is projected. It is not in a plane. It is on the space. Okay, so this p, you can write it in this manner as well. That is, your p is equal to square root of px square plus py square plus pz square, isn't it? Like, you have to remember you are playing in a phase space. That means your axes are px, py, pz, or in simply you can say momentum space. Okay, actually phase space and momentum space have a small difference. So okay, still you can consider it as a momentum space. So in the momentum space you have axis as px, py, pz. Generally in a Cartesian coordinate system or in a Cartesian in configuration space, you have x, y, z, and if you have any vector here, any general vector r, then how you write? You write square root of x square plus y square plus z square. Similarly, in a momentum space, this vector linear momentum p, you can write it as square root of px square plus py square plus pz square. Isn't it? Am I right or no? I think you understood what I mean. Now, I will use this expression in order to find out my d epsilon and g epsilon. That I am going to do. Okay? You understand the things? So I will just remove it because I have a lack of space. You just keep in mind this you need later on. Okay? Or okay, I will try to write it here. So p is equal to square root of 2m epsilon. So or p square is equal to 2m epsilon. Okay. Now you can just differentiate it. If you differentiate it, what you will get? You will get the expression for what called dp and p. P already we have, and we will get the expression for dp. Okay. How to get it? P square is equal to 2m epsilon. Then if you differentiate it, 2p dp is equal to 2m d epsilon. So you can remove the 2 and the 2, and the dp is equal to, now the dp is equal to, here instead of p what you have to use? You have to use square root of 2m epsilon. So m d epsilon divided by square root of 2m epsilon. Okay. So this is m d epsilon by square root of 2m epsilon. Now if you rewrite it, you can simplify it basically. So the final expression dp is equal to m d epsilon by square root of 2m epsilon. Okay. So since each momentum magnitude p corresponds to a single energy epsilon, because for each momentum you have a single energy epsilon. The number of energy states g epsilon d epsilon here. Okay. G epsilon d epsilon between the energies E and E plus epsilon and epsilon plus d epsilon is the same as the number of momentum states g p dp between p and p plus dp. Okay. So actually for our convenience we are making use of this momentum space. So we want to know g epsilon d epsilon, that is a number of what is called the energy state between epsilon and epsilon plus d epsilon, because each momentum is corresponding to a single energy value epsilon. So instead of finding the number of energy states, what we are going to find out? We are going to find out the number of momentum states v of p dp between p and p plus dp. Okay, that's it. So or basically you can write like this. I think this side we have a light issue, so I will write it here. This will make it short here. So I am writing it here. So what we said, g of epsilon d epsilon is the same as or equivalent to finding out g of p d. Okay, that only I told. Okay. Now, what we have to know? We have to know the number of momentum states between the linear momentum p and p plus dp. Or basically, In the moment and space, you want to know the volume of this spherical shell. Okay, you need the total number between this P and P plus dt. That means you basically need the number of momentum states between this area. Okay, so what about the volume of that spherical shell? Volume of that spherical shell is surface area of that spherical that sphere multiplied with that small thickness dp. So we have what is the surface area of this sphere having linear momentum p, that is 4 pi p square, 4 pi p square, then 4 pi p square. Then if you want to get the volume, that is multiplied with that small thickness, that is dp. So 4 pi p square dp. So this is some constant, so we can just take it as another constant b, okay, instead of keeping these numerical values. So you can write g of epsilon d epsilon, or simply g of p dp. It is equal to b, I am taking this as constant b p square dp. Okay, now we are getting into our goal. What actually we need this one. We played all these things, or we went to the momentum space in order to get the g of epsilon d epsilon, because the rest of the things we know. Epsilon, this is the energy of that particular state, and it is absolute temperature, and kb is the Boltzmann constant. This all we know. So now we will just replace it here. So we can write n of epsilon. So before that we will just again come back to our energy. Instead of p, we will write everything in terms of energy. That is easy because we already have the relation between p and epsilon, the energy level epsilon. So we can just write it as b times p square. What is p square? P square is 2m epsilon. And what about the dp? Actually, I think we kept the dp here, and I just removed. So instead of dp, I will just write it the expression. What is the expression for dp? M epsilon divided by square root of 2m epsilon. M d epsilon. Sorry, not epsilon. M d epsilon. Okay, m d epsilon divided by square root of 2m epsilon. So that was the expression for p square and dp. So now you got g of epsilon d epsilon. So I just replace this here, and you will get it n of epsilon. So I am just removing it, and we will go further. So I am just writing n of epsilon, number of particles having the energy, number of particles having the energies between epsilon and epsilon plus d epsilon. That is equal to, I have to write it not simply n of epsilon d epsilon. So that I have to write. So, okay, n of epsilon d epsilon is equal to, you have already one constant a and the constant b. So I am just writing constants separately. Then here 2me is on the numerator and square root of 2me on the denominator. So you can remove one, and there is a 2 here, root 2 here. So we will just take everything in consideration. So square root of 2 m raised to 3 by 2, because m raised to 3 by 2, because you have 1 m here as well. So m square on the numerator and root m on the denominator. So you will get that m raised to 3 by 2, then root e, sorry, not epsilon, I'm just making mistakes, okay, epsilon, then remaining is e raised to minus epsilon by kBt d epsilon. So this is the number of particles having energies between epsilon and epsilon plus d epsilon. Now if you want to know the total number of particles, we have to integrate it. So before that we have two things here. So that two things also we have to find out. So this a and b, a is a constant, b is a constant. So obviously the multiplication of this is another constant. So I am just calling it as c. Okay. So this is c into square root of 2 or root 2 also we can just consider here. So that is the total is c. A into b into root 2. So these are all constants. So I am taking it as a constant c. Okay. Then remaining m raised to 3 by 2 root epsilon e raised to minus epsilon by kBt d epsilon. So this is the expression for the number of particles having energies between epsilon and epsilon plus d epsilon. So how to find out the constant c? So that is very easy, because we defined or we considered the total number of particles capital N. Capital N is the total number of particles. So whatever may be the energies, the total number of energies on the total number of particles in the system is capital N. So we can just simply integrate this from 0 to infinity. That means the total energy, all the energies, not only the energy epsilon or epsilon plus d epsilon, you are integrating from 0 to infinity. That means all the energies possible. So that is equal to this total number of particles N. Okay, you got the idea? So I will just integrate it. So that is total N is equal to integral 0 to infinity N of epsilon d epsilon. Okay, so this will be equal to, I am taking the c outside, and also actually m also a constant. So I forgot. You have to club m also here, because m is the mass of the particle, that is a constant value. So you can take it inside. I'm sorry. C. So now c integral 0 to infinity root epsilon e raised to minus epsilon by kBt d epsilon. So if you know the integral of this, you will get the value of c, because n is you know the number of particles, total number of particles, and you have to integrate it. Actually, integration of these particles, this is not that much easy, but in physics, in the mathematical physics, we study the gamma functions. So gamma functions are some special kind of gamma and beta functions are there. These are some kind of peculiar functions, and they have some standard integrals. Okay, so this is one gamma function, and it has a standard value. So just keep in mind, integral 0 to infinity root x e raised to minus x dx is equal to 1 by 2a square root of y by e. So this is a standard integral. Okay? So nobody is going to integrate these things in our daily uses, because these are all standard integrals, and it has a standard value. Okay, like if you are going for what is called molecules and all, they have some standard atomic number and all those things. So in mathematics there are some standard integrals. These standard integrals, direct integration is a bit difficult, but you can just make use of what is called your standard integral. Okay, so just we will make use of it. And here you have to remember, here instead of x you have epsilon, and instead of a you have 1 by kBt. Okay, so we will just substitute it here. Instead of x you have epsilon, and instead of a you have kBt. So what you will get the final? So just keep n is equal to capital N is equal to, you will get the final answer as c by 2. You can cross check it at your home. C by 2 square root of pi. Okay, square root of pi. Then you have kBt raised to 3 by 2. Okay, so that is your n. So your c is equal to 2 capital N divided by root pi kBt raised to 3 pi. Okay, so now you got the constant c. You may rewrite it in a different way, like just multiplying with the pi in the numerator and denominator. Then you will get 2 pi n pi kBt raised to 3 by 2. Okay, so now we will go to our distribution of energies. Okay, number of particles having energies between epsilon and epsilon plus d epsilon is equal to, instead of c, or is it c, you will keep this one, that is 2 pi n divided by pi kBt raised to 3 by 2. Okay, then root epsilon e raised to minus epsilon by kBt. Okay, kBt, not dx, because no, we have to keep d epsilons. We have to keep d epsilon. So this is the distribution of particles, number of particles having energy d epsilon. So we can just make a diagram of distribution of particles with different energies, because when you keep the energies epsilon, kBt, or 1 kBt, 2 kBt, 3 kBt, how the number of particles that changes, okay, from this expression. So it will be like this will be like you can write, this is n of epsilon d epsilon, and here this is epsilon. Okay, I am not writing this is for an arbitrary gas, not for a particular gas. Almost all the gases obey the same kind of trend. Almost all the gases which obey the Maxwell-Boltzmann distribution function, they obey the same kind of graph. So it will be like okay, yeah, not exactly, because we will just pick it here. Okay, like this. Okay, I'm sorry. And this integral that you have is somewhat like this, the area of this one. So this is This is n of epsilon d epsilon. So here you have kBt, 2kBt. Okay, this most of the particle focus is almost having 1 kBt around here, 1 kBt, then around 2 kBt, 3 kBt, like that. Okay, so this graph and all this is more beautifully drawn in our textbook, so you just look at it. Okay, so this is the distribution of energy, molecular energy distribution is like this. Okay, now we will go to the average molecular energy. If you want to get the average molecular energy, what you have to do, you have to multiply the distribution of energies with that the energy, then you have to integrate it throughout from 0 to infinity. Then you will get the average energy of the molecule, or average molecular energy. Okay, that what you have to do, you have to consider the number of particles having energies between epsilon and epsilon plus d epsilon. Then you multiply with the energy epsilon, and after that you integrate it from 0 to infinity. So that will give you the average molecular energy. So I think it is better to make another video for that, otherwise it will be bulky.